So we can start the record. Okay, hello everyone, and welcome to the final day of the European Einstein Toolkit meeting. Today we will have very important talks, three invited talks and two student talks. Our first talk is on gravitational wave modeling for compact binary mergers, and it will be given by Dietrich. Tim is a professor at the University of Potsdam, and he is an expert on numerical relativity and gravitational waveform modeling. So, Tim, you can start whenever you're ready, and I'll let you know when you have 5 minutes left before the questions.
Okay, thank you very much. Thanks for everybody who was already here. So I was asked to give an update, a discussion, or review to some extent about waveform modeling, in particular for binary neutron star cases and for black hole neutron star cases. And of course, within the Einstein Toolkit meeting, I tried to focus on the connection towards the numerical-relativity modeling, and also trying to answer the point and the question, why do we need, in addition to cool numerical-relativity simulations, also waveform models to analyze real data? And with this motivation, I want to start a little bit. And first, I want to look at the anatomy of binary neutron star as well as black hole neutron star signals, in putting them in respect to the black hole systems, which have been studied, I would say, in more detail than both binary neutron stars and black hole neutron stars, and just to show what is the difference and where do we have to be careful when modeling these kind of systems. So in the binary neutron star case, we have, we start early on in the evolution, so we have a very, very long in-spiral. And one issue with numerical relativity simulations is that we can cover only the last, at most maybe 20 or 30 orbits before the merger, so some last few cycles, then the merger itself, and then the post-merger phase. In the in-spiral itself, we can think about it very similar to the black hole case. So most dominant are actually the masses of the objects and the spins, but also because we're dealing with neutron stars, and you had talks about the equation of state and so on, the tidal differability and other effects, not just the tidal differability, but also the resonant modes and other things, can enter the game in the in-spiral and can change the waveform model. So this is something, when later on we want to model it, has to be taken into account. Then we have this post-merger phase, which can be quite different compared to black holes, because black holes, they emerge, they have the ring down, everything is nice and easy. In the binary neutron star case, there are different varieties of things that can happen, which mainly depend on the mass. So if the mass is very high, you form a black hole right away, or black hole with a slight small disk. If the mass is not too large, then it's possible that you have, also as shown here in the signal, some post-merger remnants surviving for, let's say, tens of milliseconds up to hundreds of milliseconds before it then forms a black hole. And if the mass is even lower, it's possible to form a massive neutron star, which is stably rotating for the rest of its life. Most of the cases, you will form a black hole, and then you have the ring down, but the ring down has, in addition, some potential matter effects compared to black holes. What I mean with this is, of course, you form a black hole surrounded by an accretion disk, and there's still mass falling on the black hole. So it's not the clean ring down that are known from black hole mergers, where you just have the quasi-normal modes. These can be changed here, depending on how massive the disk is and how much mass still falls on the object. And in comparison, the black hole neutron star case is very similar, modulus of effects, that more or less you don't have this post-merger. You have still the in-spiral, which now depends, of course, on all the black hole quantities, but also on the quantity of the neutron star, describing its tidal deformation, maybe its resonant frequency, and so on. And here's, for example, a case where the neutron star gets disrupted, and then you have this extended matter tail that falls onto the black hole. And also here, this can lead to a different ring down signal. One is to say that overall, given the lower masses of binary neutron star and black hole neutron star signals, in particular for binary neutron star signals, the ring down is really at such a high frequency that we'll likely not see it at all in gravitational wave detectors in the next, 50, 60 years. For black hole neutron star cases, it really matters how massive the overall system is. Maybe there is a chance of indeed seeing the ring down, and then likely for sources where actually no matter effect is really present. So this is what we have seen so far, still in the motivation phase, that we have had about 200 compact binary mergers. And of course, we want to understand the ones with these orange dots here. These are neutron stars merging with another neutron star and then forming either a black hole or a neutron star merging with a black hole, forming another black hole. So if you go through the catalogs of LIGO and Virgo, you have, depending on how optimistic you are, between 1 up to 3 binary neutron star cases that have been seen, and I would say between 2 up to 3 black hole neutron star cases that have been seen. So this is a significantly smaller subset compared to the huge variety and huge amount of binary black hole mergers that have been seen. But this is where we stand now, and the main issues really to motivate why waveform models are needed is, on the one hand, that if we analyze these kind of systems and we compare the first binary neutron star merger event, which was observed for a minute or even up to 2 minutes, we see already the issue that it's significantly longer because of the lower mass compared to binary black hole mergers. So we have to model this system for thousands of orbits to have an accurate description throughout the entire inspire that we can measure. And when we want to compare to observational data, we can't just evaluate this once, so do one simulation and then have the source parameters, but we have to model this a few million times to find the best matching parameters to the observational data. So this is the main challenge, namely that we can't run simulations here. And given the complexity of the systems, approaches that are used for black holes, where you have gigantic databases of black hole waveforms and you interpolate between them, we are also far away from doing this in the binary neutron star and black hole neutron star land, I would say. And here's a signal that is just a minute long, or if you start at a lower frequency, 2 minutes long. In advanced LIGO, if you just look in the future, this system, this scenario gets even more problematic. Here's now the gravitational wave strain, so the amplitude of the measured gravitational wave signal in the frequency domain. You see here in dotted case the LIGO sensitivity, where the strain is above the sensitivity curve for, let's say, in the future, 20 hertz or 10 hertz up to a few hundred hertz. For the Einstein telescope, this is, of course, significantly longer, and these inspires will not just take a minute, but can take up to several hours. And of course, running these kind of simulations is then unfeasible. So we need other models, and this is now where waveform models come into game. And this is a connection of, in the early part, a point where the stars are still, let's say, well separated, have a large distance. And then, of course, perturbative methods have a chance of being successful. I guess all of you know this post-Newtonian theory framework, where you basically recast the equations in a way where you extend it for, as a power series expansion for small velocities, so expand around the zero velocity, and for large distances. So whenever the objects are separated well and have a small velocity, which is the case when they're far away, then you can use post-Newtonian theory. Deriving analytical approximations is, of course, a huge endeavor. It's very hard. But if someone is smart enough to do so, then what comes out at the end for the waveform is just an analytic expression. You can put in your numbers for the masses, and you get a waveform out in a very short amount of time, because it's just analytical. But this fails if you go to the last stages, because this does not incorporate all the nonlinearities. Of course, does not incorporate what happens when the matter comes into contact, because you have to make the assumptions that they are well separated. This does not allow you to describe this post-merger effect. So here, this is the regime where numerical-relativity simulations are important. So you see that you have basically a mismatch between the early inspire, where you have analytical methods that you can use, and the last stages, which you can simulate with numerical simulations. Of course, we would love to simulate all of these with simulations, but this would just take decades or centuries on supercomputers to just compute one long gravitational wave signal like this, which is completely out of question. So the point is that we have to combine this, and there are two different approaches. One approach, which personally I would say is a more theoretically motivated one, is that you use ideas on the one hand from quantum mechanics, but also on the other hand from classical mechanics, where you have the two-body problem and you map this two-body problem in an effective one-body problem. Here you have a relativistic two-body problem with a space-time and symmetric, and you just transform it in an effective one-body approach where we have an effective metric, and in this effective metric, we basically have a point particle moving around, and you describe the system, which is significantly easier, and then you can actually map this back to the real relativistic two-body problem. This approach allows you to cover all the, up to the inspiral more or less, up to the merger. And the other approach, and you will see a number of waveform models later on that use either one or the other, is an approach where people have, let's say, an educated guess on which function might describe the waveform in a sufficiently accurate way. And then they calibrate all the unknown parameters to either effective one-body waveforms to numerical relativity data, or they also incorporate the post-Newtonian knowledge. So it's a little bit of a mixed bag, but there is no strong underlying theory around this. This is more proof that if you have some functional form with free parameters, then you can model the gravitational wave signal accurately enough. The advantage is that if you, of course, choose a function that is fast to be evaluated, then these models are very fast, and you can compute these very long signals if you have to, which is an advantage over the EOB, where you need to do extra steps to actually speed everything sufficiently up to make it usable to analyze the real data. And now the question how the numerical simulations really enter the game. And let's say we have a waveform model, and for the phenomenological one, I will describe later on a little bit how you calibrate them from numerical simulations. Either of the waveform models, whatever you prepare and prefer, you can basically make a prediction for given masses or whatever, and you get a waveform. And here's just one example. In orange is, for example, an effective one-body model for given masses. It's an unequal mass, non-spinning binary, just a merger. And then you run your numerical relativity simulations for these setups. And this is shown here in black. And then you see that you can compare the waveform from the theoretical prediction with the numerical simulations. And you see that in the early part, all agree very nicely. Of course, it's already an older work a few years ago. And you see, it's nicely visible, that the orange dashed curve is this prediction from EOV, and the numerical simulation at the last part slightly start to deviate. You might ask the question, does it matter, this small deviation, yes or no? The point is, it clearly will depend on the loudness of the signal that you will see. But important also that these last stages, and you see here the density profile, is actually the point where most of the fun stuff happens. So this is the point where we can extract information about the equation of state and so on. So where we need accurate models, otherwise we will, I show this on the next slide, get biases. And so you compare your numerical simulation basically with a model, and you can either confirm this if all agrees, or if it doesn't agree, then you can try to get good simulations to recalibrate free parameters, as I will show later. So overall, these models can be improved by new analytical knowledge, which comes from post-Newtonian theory or whatever you think is most applicable. It's a huge endeavor, but it's really important. Then you can add additional physics. Also there you had already talks that covered this a little bit, and you will have later today. For example, if you have resonant modes of the neutron stars, if you incorporate these kind of things, you make your model physically more accurate. So you improve your model and you add more physics, which can be very useful. And last but not least, and the most important for the rest of the talk, is basically you need better NR data to actually do better calibration. Because in this plot, what I, of course, completely ignore is that this black curve from the numerical simulation is not the true answer, right? All our numerical simulations have an error, and we have to quantify this error very accurately. Otherwise, it might be that we see a deviation between the prediction of numerical simulations and the waveform model, and it's not the waveform model that is performing poorly, but our simulations are just. And now to the question whether all this matters, and where we stand with our waveform modeling and understanding. And this is the case to study mock data, which we did. So basically we used one of the waveform models. We'll show later which ones exist. And we tried to answer the question, which goes back to the talks I think that you had on Tuesday, what is the correct equation of state? Or here, what is the correct radius of a 1.4 solar mass neutron star? And this is a dashed line, correct, because we create the data. So we know what would be the correct answer. And then we use the same model, waveform model, for creating the data and for analyzing the data. And you see that the error decreases with 1 over square root of the number of detections, and it actually converges to the solution or to the value that you put in, which is what you expect. If you use a different waveform model, those models that are actually used for analyzing data, you see that after, let's say, 10 or 20 events, you get a bias, which is larger than the 90% confidence interval that you quote. So which means that since in reality we don't know the correct answer, we would actually measure something off. If you recall what I showed in the second slide, so how many BNS mergers we have had, we are more or less here around 1 or 2 events, which means that so far our uncertainties in the waveform model are all good. We shouldn't worry too much. But of course, in the future, with future detectors, then we will not have just tens, but hundreds or thousands of events. And this means that in the next, let's say, 10, 15 years, there's a huge amount of extra work to do. And this can be done by incorporating better numerical-relativity simulations in your waveform model calibration. And here I want to start really by focusing on the INSPIRE and want to address the 2 questions of what are the existing challenges on the numerical-relativity side. So how can we get better numerical-relativity data that then can be used to calibrate actually the waveform models better? And this is now a completely subjective statement. I think that the 2 big challenges are, on the one hand, really covering bigger regions of the parameter space. In other words, if you want to use a model, even in astrophysically not so relevant regions, maybe large mass ratios for the neutron stars or so, you still have to have a very good and accurate model there. Otherwise, if you want to rule out that these things have not been measured, you can't do it without having an accurate description in this region of the parameter space. Otherwise, you get biases and you don't know, is this your waveform model or is this really that the systems might exist or might not exist? And second, of course, you have to have a well-quantified error analysis and error for your numerical simulations. And as I said, let's look first a little bit on the INSPIRE. Regarding this coverage of the parameter space, one can say that the community put a lot of effort in starting to simulate eccentric systems, in precessing systems, spinning systems. You see here these high mass systems where they have the merger and then no post-merger phase, high mass ratio simulations. So there is a coverage of the parameter space, but the coverage is still rather poorly, right? So there are a few high mass ratio simulations, I don't know, maybe 5 throughout the world, eccentric simulations, I don't know, maybe also 10-ish or so. Precessing simulations, I think there are just 4 on the market that people did. So there are not so many simulations in different corners of the parameter space. Of course, most of the time we focus on regions of the parameter space that are astrophysically more relevant. So for systems that we expect are there, but as I said, we have to cover the other things as well. And it also always matters what is the focus of our study. So we had talks yesterday by François and David and so on, focusing also on the microphysics. If you deal with the microphysics and the post-merger stage, of course, you don't want to have a super long INSPIRE and so on. So you don't produce your numerical simulations actually for the purpose of creating waveform models. So it really depends. We have more simulations looking at the microphysics, and these are not really usable for calibrating waveform models. But nevertheless, there are more and more waveforms I will show that can be used. And here, an overview from the recent work from Alejandra Gonzalez, where she collected a lot of simulations for the core database. And each of these points is one simulation. And you see there are a few hundreds just from BAM and THC. SXS has its own catalog. The group of Masaru Shibata has their own catalog. So let's say overall, there might be 1,000 or more waveforms, some of them simulated for multiple resolutions, which is critical to address the next point, namely the accuracy of the NR data. And also this is, of course, a non-complete and subjective list where I try to list the points that I think are actually most dramatic and most problematic in terms of modeling waveforms for calibrating waveform models. The first is the numerical discretization. More or less all the codes that are used in doing hydro simulations use either finite differencing or finite volume methods for the matter itself. Even if the spacetime might be discretized spectrally, the fluid isn't. And here you really get the biggest error in the waveform model from this discretization. So this means you either need higher resolution or some other more fancy methods that I show on the next slide to reduce this error. The next point I would say is still an issue are initial configurations. Nowadays, it gets possible to simulate, for example, spinning systems since, I don't know, 10 years or so. But just as an example, the framework or the equations that you solve there make an assumption that you ignore all higher order spin effects. And every initial data code, that it be Ascrit, Fuka, or whatever, Kokal, they use the same framework and they all ignore higher order spin effects. But if you now look at accurate simulations from the group of Masaru Shibata, for example, with highly spinning neutron stars, you see oscillations in the stars, which potentially could come from this assumption. So there are still assumptions, not just for spin, but also for eccentricity and so on, that are made in creating the initial data that if you really want to model now things very, very accurately, could reduce the accuracy of your simulation. So I would clearly put this still on the list. Then you simulate everything on a finite domain, which means that you have a finite extraction of the waveforms. Of course, you can do Cauchy characteristic extraction if you want, but this is from, let's say, these 1,000 simulations done for less than 1%. So most of the time, errors come into game by actually extracting the gravitational wave signal at a finite radius. But these errors, I think, I'm quite convinced they're significantly smaller than the other ones. And then, of course, you also have sometimes mass conservation violations due to the artificial atmosphere around the neutron stars. But also these effects are, if you then look on the imprint of the dephasing, significantly smaller than the ones listed before. So this is really, in my opinion, a list with decreasing importance. So the first bullet point, the numerical discretization and an accurate method to describe the fluid, is really the dominant one which has to be addressed. Here just an overview of the last few years, what people did to improve their simulations. One work by Radici and also Benuzzi, where they had the idea that if you have the hydrodynamical framework and you want to do this hydro simulations, then you are not just solving the Riemann problem with your primitive or conservative variables, but you go into the characteristic scheme. So you match basically along the characteristics, you solve your Riemann problem there, and then you go back to the system that you evolve. If you do so, you actually can have a higher order of convergence than compared to not doing this. What's shown here is that phase difference between different resolutions, shown here with different colors, low minus medium, medium is high, high, and then to the finest resolution. The larger you go in the resolution, the smaller gets the dephasing between different resolutions, which is also clear. You can compute the order, and if the order is very, it's clear convergence order, then you can use Richardson extrapolation to get an even better effect and then better guess. And in this plot, therefore, it's so nice. It's also shown that if you extract your waveform at a finite radius compared to an infinite radius, this is here the dashed dotted line, you see that this is actually the error which dominates at the early inspire, but this is a logarithmic plot, so it's below 0.1 radian. While later on, over time, the numerical discretization comes in and around the merger, then dominates compared to the other waveform error. So this characteristic transformation is one way of getting a better approximation. Another one was, as I recall if I recall correctly, first done by Most et al. In 2019, where also for the flux computation, you're not using just the normal flux, but also the derivative of the flux operator. And he showed in his work and one work later on that this can also improve the accuracy by getting a higher order convergence. And then you need not as high resolutions to get the same waveform error. Then a few years later, there was an approach using an entropy limiter. This is the first work was not by Dulles, but by Garcilena, where it was the idea that you can basically map where you have the highest entropy, which you assume is around the star surface, where also this high resolution shock capturing methods from the first two approaches are so important. And you just add some artificial viscosity there. And they showed also that you get a higher order convergence. And recently, also Kenta Kiyuchi had the approach of saying that, okay, let's use a more complicated Riemann solver. And he showed very accurate long simulations, which shows also a higher order convergence and shows smaller phase errors. These are basically the things that I have in mind when I think about how to model waveform models more accurately. Of course, these are all technical and I don't want to go into the detail. I just want to say that people try to address this differently. Some methods are more robust than the other ones, but generally there's a huge trend and a huge wish in the community to decrease the phase error in the simulation, but also to provide an accurate description of the phase error. So what you hopefully see here nicely is that this is a simulation done by two different codes. It's the same initial data. And I think this is also important to highlight that one way of quantifying whether there are errors is you have to run with different codes the same setup and then compare. There are different code comparison approaches that have been done over the last years. This is between the SACRA code and the BAM code using a very highly spinning system with a dimensional spin of 0.5. So this is really a millisecond pulsar that is out there. I hope you can see this gray shaded region here, which on one screen I can see and on the other not. This is actually the estimated uncertainty by looking at different resolutions and then doing the Richardson extrapolation. So you see that, of course, different codes produce different uncertainties. But generally, I can say that if you cross-compare the BAM and the SACRA data here, they all fall in the same region and agree very well within their uncertainty. And now it's a comparison with all the waveform models here, the setup of waveform models, and they all disagree strongly, I would say, around the moment of merger, which is one point where it shows that, okay, you manage to get higher accuracy simulation by smaller errors. For example, SACRA really uses here this higher order Riemann solver. And then you see that in given regions of the parameter space, the waveform models that we have are just improvable, let's say that this way. So there is clearly a strong dephasing. You might argue that spin of 0.5 is too high, astrophysically, which might be true, but still we need to improve in these regions, certainly. And now, because I was asked to talk about these waveform models, I want to show one slide, which clearly shows that people doing waveform modeling are very innovative in giving names. And that if you're not doing this, then you might be buried by a huge amount of different waveform models. So I tried to look up all the waveform models for binary Newton stars, which have these potentially cryptic names if you're not used to, but I tried to put them into, let's say, 5 categories. And you can ignore all the ones in basically all the exact names. Just remember the categories. So on the one hand, we have purely analytical models going back to post-Newtonian theory, which I can say nowadays is not used really for waveform model analysis anymore, because it's getting too inaccurate around the moment of merger. Then we have the effective one-body approach that I mentioned earlier, and I grouped this in 2 different classes here because these are, let's say, 2 different approaches of how to do this remapping, how the resummation as well as different. So there are different flavors. One is developed by the people at the Max Planck Institute, so the division of Alessandro Bonanno, and this is basically developed by people around Thibaut Damour, Sebastiano Benuzzi, and Alessandro Nagar. So these are different flavors of the EEB model. And then you see here a huge amount of list of phenological models where basically you always have at the beginning a black hole model, all these IMR phenom, and also the SEB ROM is all these black hole, and then underscore and a title are all these phenological descriptions by just adding title effects. And this is all, and for now you can just ignore these names, and we can go on and describing basically how you can use NR simulations to calibrate your waveform model, and why also it might be important to get more accurate simulations to calibrate better. And of course, this is a personal bias nowadays that I talk about the phenological model. And I will focus purely on the title description, because what we do, we have basically this waveform in the frequency domain. So this H tilde is the frequency domain waveform, where we have an amplitude and the phase. And motivated by post-Newtonian theory, we say that, okay, we can split up the phase into point particle contribution, a contribution where we have a spin orbit interaction, a spin interaction, cubic and spin interaction. You can go even further on. But we talk about neutron stars that deform, so we just focus on this title description here. So our purpose and our aim now for the next 2 minutes is actually understanding how we model these tidal effects with a phenological approach. And for this, I focus on the newest waveform model in this family, which uses going back to the amount of waveforms that are there, 55 waveforms. So from this huge list and from also other, let's say, databases and so on, only 55 waveforms were used. And just to put this into perspective, for the version before, so with the version 2 and for the version 1, only 3 had been used. So the number of waveforms that are used for the calibration is significantly smaller than for black holes. So here we have these 55 simulations, and what we do with them is we have the NR data, which is shown here in blue, and this is, for example, simulation data with the Sakura code from Shibata et al. And then we stitch this together with an effective one-body model, so this is in orange, and we create a hybrid waveform going very early on, having thousands of orbits, and then in the last part, switching from the EOB model to the numerical relativity data. And then from this, we subtract if you go back, we subtract basically all these other contributions to just get the tidal contribution. And this is then shown here, the tidal contribution as a function of frequency. 0 means infinite separation. Omega merger is basically the merger frequency, and you see the frequency, the phase increases over time, the absolute value, and then you have here the merger. So we try to model these kind of things, and here different approaches on how to model this, shown with a dashed line or dotted line and so on. So we have our tidal phase, okay? And this was in the time domain. Here we have it in the frequency domain. And now comes the magic of the calibration. You basically make an ansatz. And this is what I said about you are free to choose whatever ansatz you think is an educated guess. Here it's that you say, again, motivated by post-Newtonian theory, you have some love number, so basically some quantity that determines how much the neutron stars deform. It's here frequency dependent because resonant effects and so on are also incorporated. You have some prefactor from the Newtonian description, some x is proportional to the frequency, and then you have some function, and the function that we choose is just a rational function. How many coefficients you have and so on is purely your choice. I mean, this is a choice made after, let's say, several attempts. Then these ends are to some extent already fixed by post-Newtonian theory, or the ends, if you split them up and then you incorporate mass ratio dependence and so on, end up in free fitting parameters. So there are about 10, 12 fitting parameters. And these 12 parameters, you then fit to your 55 simulations and the phase descriptions. So these, let's say, 12 parameters are completely free. You try to find numbers, and then you try that your, let's say, fit prediction is actually agreeing with the extracted data that you get from the numerical simulations. If, of course, you have a larger numerical error and this gets shifted to one way or the other, then this gets problematic because you would just fit noise, which you don't want to do. But in the newest case, and later on, you use other waveforms for the comparison, and you see that here's the dominant mode. You see this time the numerical error is smaller, is larger than the comparison with the waveform model for this particular case. And whenever you have models with this HN inside, this means this model also has higher modes. So instead of just looking at the dominant mode, you can also look at all the others and see whether you now have developed a waveform model that agrees in these other modes. So this is the status, the state of art, more or less, for in-spal modeling from the phenomenological side. Of course, as I said, you also have the EOB side on the other hand. How about the post-merger? The post-merger, one can happily say, is a slightly larger mess. So there are only a few clear things where people, I think, are happy on agreeing on. And this is that in the post-merger phase, you have characteristic frequencies. And the characteristic frequencies mainly depend on the mass, on the equation of state, so on the tidal deformabilities indirectly, on the spin and so on. And you have different effects that can shift this around. Thermal effects, magnetic fields, presence of spins, how to incorporate the neutrino physics and so on. But clearly is you have some clear feature and some dominant frequency, and this is also shown here. You have some frequency in the post-merger phase that dominates, and this is currently what people try to model first, and then they try to attack more or less the modeling of subdominant peaks. And here's a spectrogram from an older work by Luciano Rezzolla, where you see that you have basically a clear main emission peak afterwards. that is clearly present throughout the time, and you have side peaks that can, and most of the time, are damped significantly earlier, but still people try to incorporate this. And this is a business which is done by a number of people. I tried to be complete, but certainly forgot people who proposed waveform models for the post-merger phase. But currently, we can say that this is a work in progress. There are post-merger models out there, but the accuracy, of course, is significantly lower than what we have in the INSPIRE. But the two approaches are either that you use an analytic or numerical description of the post-merger phase using, for example, quasi-universe relation mapping the post-merger to the INSPIRE, or a work done by Vanguard and others where you have the INSPIRE and then with, let's say, an unmodeled description with wavelets or so on, try to model the post-merger phase. So either you go with a modeling approach or an unmodeled approach and then try to dig out in the future some measurements from the post-merger that you have. And then there's a huge amount of things that you can do if in the future you might have seen a post-merger waveform. You can first address the equation of state hot matter, but what you can also do is some consistency tests, and the only thing I want to show about the post-merger. Yes.
You have 5 minutes left.
Yeah, perfect. So here's, for example, a description of, let's say, the function theta, which is a function of the tidal deformability and also of the mass. And as this function, you can basically then compute from numerical simulations the main emission frequency after merger. And this is a prediction which holds from the simulation, but what you can do with potential data, and this is of course also map data, you measure something from the INSPIRE, you get some prediction, what you think for the theta value, you can compare it to the quasi-universe relation and would get some estimate for the post-merger frequency. But if you measure the post-merger with a signature share of 2, 6, or then later 10, you will be able, and this is similar to this test of general relativities with pulsars, to see whether all agree at the same bullet point and are consistent with each other. If they wouldn't, then this, of course, implies a huge amount of interesting physics. Either your universal relations are wrong, which I think is the most likely scenario if you find a disagreement, or you have to incorporate some new fancy ways of dealing with the nuclear physics inside neutron stars, or you have a violation of GR, or this would be possible. But these consistency tests can only be done once you see a post-merger phase and the post-merger signal. And now in the last 3 minutes, black hole neutron star waveforms, because you might argue black hole neutron star waveforms are very similar to binary neutron stars, which is the case. The phasing is the same. You just say that one object, instead of being a neutron star, is a black hole. And then the main difference is the amplitude, actually. You see, these are dedicated black hole neutron star waveforms. They are significantly less than for the binary neutron star case, because you can just set lambda to 0. But you have to deal with the amplitude. So here's a comparison, again, in the frequency domain, where you have frequency, and here's the frequency domain amplitude of the waveform, where from the black hole model, where you have this nice ring down, if you have, for example, a disruption of the neutron star, you shut off your waveform earlier, so you do not reach these high frequencies, and exactly this shift has to be modeled. In gray is here the NR simulation, and in black is here, for example, one older, already 5-year-old waveform model for black hole neutron stars, which is still currently used for analyzing the data. But there are newer models also that are currently developed with newer waveform models and so on by the group by the Mallorca group in UAB, and also with higher modes trying to incorporate basically better description of the neutron star black hole modeling or systems. And the last caveat is that also for these models and so on, the issue is again the parameter space coverage. Here's a simulation movie of a sub-solar mass black hole with a neutron star. The sub-solar mass black hole disrupts the neutron star and then happily moves away through a kick. And you can also compute the waveform for this. The numerical-relativity simulation waveform is here done shown in black. It's work by Mark and et al. And then you compare to the waveform models that you have, and you see that there's a huge disagreement, which shows that in these regions of the parameter space that are completely extreme, current waveform models, and I can say that also the waveform models that are currently under development, will perform very, very poorly. So there's still a lot of work to do in the future. And to my summary slide, so the NR simulations I showed, hopefully in a nice way, are useful for testing, but also for calibration of waveform models. And we need these models to analyze the data. There are a number of challenges to get accurate simulations, getting correct initial data, doing the parameter space coverage and so on, but mainly getting the phase error to an acceptable level. As I said, the previous phenomenological models just used 2 to 3 waveforms because there the error was under control, and for the others just too large. And nowadays there are numerous models with different flavors and so on. And so far we are, I would say, not dominated by systematic effects in the waveform models, but in the future this will clearly come with the next generation of detectors. This is it for my side.
Thank you very much, Tim, for the very nice talk.